It's a great pleasure to be here and to follow Matt. So unfortunately, this lecture won't have any cute graphs like Matt's. I'll have a few graphs later, but not in this lecture. The other sort of thing that's complementary is that Matt actually gave a great introduction to sort of coming from the viewpoint of networks and how they're going to be useful for thinking about a range of economic and social interactions. So I'm going to start actually from the other way around. I'm going to start from a very simple but pervasive problem in economics. It's that we think about externality. So it's already a huge area within economics to think about various different types of externalities: productive externalities, social externalities, informational externalities, peer effects. And what I'm going to try to argue and develop it from that angle is that networks are actually both a powerful language for thinking about these sorts of externalities and actually implicitly part of any investigation of such externalities. And being more explicit about that both makes it more useful and gives us perhaps some additional ideas. And in the process, several important topics on which many people in this room actually have worked are going to come back to the surface here. So the plan is I'm going to talk a little bit about using networks for a language for externalities. So then I'm going to immediately jump to games over networks, and I'll motivate why, in my opinion, actually for almost all of the externality type empirical and theoretical investigations, you cannot avoid the issue of games over networks. So I'm going to spend a bit of time going through an equilibrium of games over networks, and then I'll talk about identification problems and then ways of dealing with those in the context of empirical approaches. And I'll then talk about a specific application that illustrates some of these issues. And then I'll end with a couple of important observations about not because I'm saying it so, but important from the viewpoint of the limitations of what I've covered on thinking about endogenous networks. So let me take a particular topic that I know a little bit about, which is human capital externalities. And there are many, many papers and important works in economics, going back to Marshall's Principles of Economics, Lucas, Jane Jacobs, Rauch, and so on. And all of these specify certain types of externalities. But actually, when you look at the details, the externalities are different about who the originator of the externalities are and who who the receivers of these externalities are. For example, Lucas writes down an endogenous growth model where anybody who has human capital creates human externality on everybody in an equal manner. In Marshall, human capital externalities are from workers to others within the same industry. Jane Jacobs, although she has different parts in her book, for example, talks about how managers across different industries in the same city create ideas externalities on each other. So you can see that, these externalities are going to be different in terms of who creates externalities on whom. So how do we actually think about this? Well, a natural way of thinking about this is in terms of a network. So we can think of the economy as consisting of n units, n workers or firms or individuals, and then we're going to have the adjacency matrix that Matt introduced. I'm going to call that G, and boldface G, in fact. And it's going to represent these networks of interactions. So differently than what Matt talked about, he hinted at this, but I'm going to be much more explicit on this, is that rather than sort of friendship-type networks, which are both undirected, which means symmetric, if I'm your friend, you're my friend, and also mostly because of measurement issues, we treat it as 0 ones, I'm going to generally work with networks that are both directed and weighted, which means that I can create an externality on you and you may not create an externality on me, and the strength of that externality is going to be one of the parameters that's going to be specified. So in particular, we're going to be looking at situations like this, where a node J is going to create an externality of strength Gij, and that's going to be our graph or the network representation in terms of a matrix. So as Matt already made it clear, it's entirely equivalent to think of a network in terms of the matrix or the graph, and I'll go back and forth between that. And so this is the matrix, and then I'll also use the ith column of G by Gi like this. And then I'm going to just adopt the convention, although I don't need to, that you don't create an externality on yourself, so the diagonal elements of this matrix are equal to 0. In other settings, there might be self-loops, but that's not really important. Okay? So let's take the very simple linear form. So we have an outcome variable y, for individual I, it's yi. It depends on his characteristic xi. So in this context, I'm going to think of xi, for example, as schooling, and yi might be your log earnings, for example. So at this level, this would be just like what is done generally in labor economics. I look at the effect of your schooling on your earnings, controlling for other things. But I'm going to allow for this effect of others human capital on individual I. So I'm going to do that. I'm going to take the column of that matrix. So the column is essentially measuring which the effects into individual I. So I'm taking the ith column and then turn that into a row matrix and then multiply that with the matrix of all of the x's in the economy. So essentially, this is a flexible way of writing what is the impact of the human capitals of everybody else on other individuals. And then there might be other controls and so on and so forth. So for instance, if we took Lucas's model in which everybody creates externalities on everybody else, all the non-diagonal elements of G would be equal to 1 or would be equal to some number. Scale is not so super important here. But if you take, for example, the specification that Marshall has, it's going to be a link only from me to other people who are workers in the same industry, in the same area, and so on. Okay. Now, Chakmansky, who is somewhere over there, call these contextual effects. So these are effects from predetermined characteristics. Now, you could also think of a different type of externality. For example, you can think that what actually I'm affected by isn't the predetermined characteristics, but perhaps I am affected by the actual outcomes of other individuals. So I can use exactly the same language here, except that here I take the inner product of the column vector gi with the outcome vector y. Now, one view is that this equation 2 is much more challenging and perhaps less natural than the equivalent 1 that I just showed you. One was this one with the predetermined characteristic, and this one here has the y. Of course, you could combine the two, or you could solve out here, do some straightforward matrix algebra, and express everything in terms of x's, of course. But conceptually, one might think that this is less compelling or more difficult for some reasons. And my colleague Josh Angres, with whom I've had several discussions on these issues, mostly disagreeing, but sometimes agreeing, for example, develops this point in his recent labor economics article on exactly this. But in fact, what I'm going to try to show you is that even if you start with this equation here and then think of this as an equilibrium thing, which we normally like to do in economics because these x's are not randomly assigned, they're not exogenous. In fact, you're going to always be mixing endogenous and the contextual effects, and then you have to think about the identification and the economic challenges in this context. So in fact, as an illustration of this, let me go back to sort of something that I did almost 15 years ago here with Josh, when we were trying to estimate human capital externalities following on the footsteps of Rauch and others, looking at the local labor market. And then, my view at the time was exactly like what Josh argues in the 2014, that the equation 1, which is where the effects are from the predetermined characteristics, is sort of easier and more natural, and perhaps we can sort of deal with that. And then we made a bunch of assumptions in the context of a simple model, and actually it turns out that those assumptions were buying us a lot. So in particular, let me illustrate that as a beginning. So what we sort of assumed there was that you maximize your log income as a function of your schooling. And what that assumption essentially gave you was that I could make my decisions independent of the schooling decisions of other people. But that was a very, very special case. As soon as you go away from a situation in which schooling affects your income exponentially, the usual sort of log wage depends on years of schooling, and you maximize log income minus separable costs of schooling, then what you're going to have is a general situation in which when I look at my best response, I cannot ignore the schooling choices of other people. So in other words, my schooling choice in best response is going to look like xi, some function of the exact externalities that are being created on me. So in some sense, even if you start with an equation like this, where the effects are from predetermined characteristics onto outcomes, from schooling to income rather than my income directly affecting Matt's income, you will end up with the endogenous effects, and you have to deal both with the contextual effects and the endogenous effects when you want to try to deal with this. So I'm going to be, this is sort of a roadmap, so I'm going to be much more explicit on this. So now to be more explicit on this, let me sort of formally introduce the outcome equation that I'm going to use in the game over networks. So I'm going to, again, look at exactly the same setup, an economy consisting of n agents. And these n agents are going to interact according to some adjacency matrix G. And I'm going to call the particular way in which they influence each other an outcome equation. And to make life simple, so here, because things were affecting through logs and exponents, etc., let me take the simplest ever possible setup you can do, which is a quadratic. So I'm going to take a quadratic interaction, which is that my xi affects yi, and then there is this interaction effect with some coefficient gamma I, and then there is going to be this quadratic term here that the extent of the externality, again determined by the inner product of the ith column of the adjacency matrix and the vector of predetermined characteristics schooling, is going to have a coefficient here in front. So in particular, let's be a little bit more specific here in terms of this equation. There is an error term here, epsilon I. There's another term here, xi. So why is there an error term here, xi, that multiplies xi? Well, as we'll see, if you don't have that error term, this would be a really weird model. So there's some reverse engineering here, but it's not a crazy thing. And then I'm also allowing a lot of these coefficients to be heterogeneous across individuals. But most importantly, there are own effects. So this is alpha I is these heterogeneous own effects. There are the spillovers, which is this gamma i's. It's the impact of the schooling of others on my education, or is the impact of the characteristics or features or predetermined features of others on my characteristics. But then there are also interaction effects that these things are actually impacting me. So I'm going to call these strategic effects. So in particular, whether this is a game of strategic complements or strategic substitutes is going to be determined by these strategic effects. So, for example, whether phi is positive or negative, as we'll see in 1 second. Okay. So I'm going to take this equation 3, and I'm going to think of this as the outcome equation, as I said, as it's written in bold, because given the x's, this determines what the outcomes are stochastically, of course, subject to the epsilon I and xi random error terms. Now, in theory, one could just take this equation and try to estimate this by some nonlinear methods, for example, nonlinear least squares. Now, what we're going to see, in fact, as we go along is that in addition to a variety of other econometric problems that have been sort of identified and emphasized in the literature, there are going to be just deeper impossibility results unless all of the x's happen to be randomly assigned. So therefore, there is, of course, always one benchmark case which none of the things that I'm saying are relevant, which is that all of the x's are randomly assigned. If all of the x's are randomly assigned, there is, of course, no game because people are not choosing x's. So therefore, the statement here that I'm going to make is that as long as all of the x's are not randomly assigned, so then there is some degree of choice, even if there are some exogenous shifters of these choices, there are going to be some important identification problems that I think networks clarify what they are, and they're also going to clarify perhaps how we might go about them in order to get to some of these issues. So, okay, now to make this more operational, of course, I also need to introduce a payoff function, and let me do that in the simplest possible way. So assume a quadratic payoff function, and in particular, since x is what I do in order to generate output, like a schooling, that has a cost, let me take that to be a quadratic cost with some cost coefficient theta, and then my payoff is linear in my outcome. So this is as I said, this is the simplest possible game. It's a quadratic payoff function. It's quadratic because it's got xi squared as a cost, and it's also quadratic because my xi and your xi's interact in a bilinear form, another quadratic term. So it turns out that this is in fact pretty much identical or a special case or a slightly more general case of a number of papers that have been written in the literature. Very interesting papers by Calvar, Mengol, Pattaccini, and Zenou on crime networks. A very well-known paper by Calvar, Mengol, Zenou, and Ballester in Econometrica on who is the key player. Work by Bramoulet, Cranton, Damours on public goods, and a variety of other papers. So best responses are pretty easy to derive here, and let me just give what they are. Since this is quadratic, you just maximize that quadratic payoff function, or in other words, you stick that outcome equation here into here, and then you just maximize that, and then this gives you the following best response function. First of all, there's a max here because X, your years of schooling or whatever investment you're doing that's creating the externalities cannot be negative, so you might be at a corner solution. But the more interesting thing is what's in here. So there is this alpha I. Everything is divided by theta because theta is my marginal cost. And then there is this phi over theta times gi prime x. So this is a strategic effect. And then there you have the error term here. So now you see why in the outcome equation it was quite expedient to introduce this error term here. If you didn't introduce an error term here, just the additive error term would have washed out when you do the optimization, and the best response equation wouldn't have any error term. And of course, no empiricist who's worth his salt or her salt would be sort of running regressions without error terms. So it's pretty useful to have this random effects here. Okay, so you can also see that phi here governs whether this is a game of strategic complements or strategic substitutes. So in particular, when phi is positive, what it means is that when that externality is summarized by the inner product of the ith column of the adjacency matrix and the vector of investments is high, then I want to do more. And when phi is negative, when that externality on me is high, I want to do less. So that's exactly strategic complements versus strategic substitutes. So in particular, this is a game of strategic complements if and only if phi is positive, and it's a game of strategic substitutes if and only if phi is negative. Okay. Now, let's first of all ignore the corner solution. I'll come back to the corner solution. So in particular, suppose that all of these x's are positive so that I can forget the max. Then I can write all of these things as stuck together as a set of equations in matrix or vector form. So it says that the vector of x's is equal to the vector of the alphas, which were these own effects that we were trying to estimate. These externalities, again written in a matrix form. So here, instead of gi, I have the entire adjacency matrix G. So I'm picking different columns of that matrix depending on which individual I'm looking at. And then the error term here, and then the error terms and the alpha, I put tildes on them so that I forget the thetas there. Now, of course, this looks very familiar. It has x on the left-hand side, x on the right-hand side. So you can rearrange things and take inverses, provided that this inverse exists. And in particular, you end up with the solution given in equation 5. So x is equal to, it depends on my characteristics as summarized by alpha and my error term. So alpha is the sort of heterogeneous characteristics, and the c's are the error terms, which are also I know before making my decisions. But all of these things are multiplied with this inverse, I minus phi over theta times g's or g transposes inverse. Now, and throughout here, I'm assuming that that inverse exists. Okay, so in fact, this is a unique interior Nash equilibrium. If that inverse exists, it's unique, and that sort of simplifies things, and I'm going to come back to it. Note that throughout, even though interior equilibria are unique, there could be multiple equilibria because there could be corner solutions. If you want to think about it in the easiest way, take the strategic substitutes case. In the strategic substitutes case, if those strategic effects are large enough, I am Matt's neighbor. Imagine I create externalities on him and he creates externalities on me. There could be multiple equilibria where in one of them he invests a lot, and because he invests a lot, I go to the corner and I invest zero. Because I invest zero, that supports him investing a lot. But there could be another equilibrium in which I invest a lot, Matt invests zero, and so on and so forth. So those kind of multiplicity could exist. For now, I'm ignoring them. Okay. Now, let's come back to the centrality measures. So Matt introduced the class of eigenvector centralities, and one specific sort of example of that is the Bonacci centrality, and essentially that's given by this expression. So the Bonacci centrality is that you take the adjacency matrix, you pick a scalar number A, for now think of it as a positive number, and then you take this matrix, this inverse, the identity matrix minus A times G, and that multiplied by the vector of ones gives you the Bonacci centrality measure. So essentially this is doing exactly what Matt did in his eigenvector centrality. What it's saying is that I'm defining my centrality by whether the people I'm connected through the adjacency matrix are themselves central. So it's the recursive notion, or fixed point type notion, because if I am central, then the people that are connected to me are central, and so on and so forth. Now, what is this coefficient A? Well, to understand what that is you take the expansion of this inverse, so that gives you, this is something I'm going to use again also in the last lecture when we come to economic interactions over a network, for example. So you can always write this as this infinite sum of the powers of the matrix. And this sort of clarifies that. What you're doing is you are taking different combinations of how I go from Matt to Kale and from Kale to Jeff and so on and so forth, but you're penalizing if these walks that go from me to you are long ones. So an A is how much you penalize it. So in particular, you're sort of putting a penalty of penalizing these long walks. If you didn't have the A, then long walks versus short walks would be sort of equivalent. Now, of course, A here naturally is like negative, but you can think of generalized Bonacci centrality where A could be negative also. Okay? So now, with this in mind, when we look at this, this has a very nice structure. It says that my investment is going to be my characteristics times my Bonacci centrality. And why is it that the Bonacci centrality, or this particular version of the eigenvector centrality, matters? Because what I want to do is I want to downgrade or upgrade my investment depending on whether other people near me are investing or not. Well, to know that, what I do is I think through about their investment, but their investment just like my investment, so it's an, again, recursive notion, so that's where the sort of the Bonacci centrality type ideas come through. And now if you want to characterize the full equilibrium, not that it's very important for what I'm going to do, but just for completeness, take the, arrange the agents such that first A agents are the active agents which have positive investment, and then partition the G matrix like this, and then you can write these Nash equilibrium such that for the active agents, this first order condition that I wrote for the interior solution is satisfied, and for these guys it holds as complementary slackness form. And then this could be unique or not. Now, whether it is unique or not, you can characterize that. Just it's the simplest way of thinking through that is actually to note that these quadratic games and many other of these games are also potential games. Now, potential games essentially mean that there exists a function, a potential function, where when you look at the derivatives of that potential function, they give the first order conditions, and the potential functions are useful both for characterization. They always have an equilibrium. Equilibrium is a solution to an optimization problem. They're very useful for computation, but they're also useful for issues like uniqueness. Why? Because since we're thinking of a potential function, then if it's concave everywhere, then it can at most have a unique equilibrium, so that's a sufficient condition. So here the potential function is this thing, and you can easily check that the this thing is going to have concave if this quadratic form here is positive definite, and that quadratic form being positive definite is again related to the eigenvalues of the G matrix, and in particular a sufficient condition is that the middle term there itself has to be positive definite, therefore the eigenvalues of the G matrix should not be very large. So in particular, the absolute value of the minimum eigenvalue has to be less than phi over theta over phi. So the reason why I'm going through this is because these are very simple conditions to check if once you have an applied problem, and then also when you come to the estimation point, you can actually verify these things. So one issue is that if you're going to estimate a model like this, if it has endemic multiplicity of equilibria, you'll have to worry about which equilibrium you're picking, etc. So one thing you can do is actually you can estimate and then check whether, given your estimates, it satisfies the uniqueness condition. So that's part of the reason why I'm actually going through that. Okay. Now, but the most important thing that I want to emphasize here is that, and this is what I said already, but now it becomes much clearer, even though we started with the outcome equation that had only contextual effects, so just like Josh and I did, in our 2000 paper, we may have hoped to get away without getting into the issue of endogenous effects. It turns out that you generally cannot do that. So going back again to this equation here, it's that actually I refer to equation 4 here, so let me do it equation 4. The special case in which I can ignore the endogenous effects is only the special case in which phi equals to 0. When phi equals to 0, this term drops out, but as long as phi is not equal to 0, you end up with endogenous effects in which your x influences me. Now, it's different than what I started with, because when I talked of endogenous effects at first, I was talking of your y, like your labor income affects my labor income. Now, you may have thought that that's a really strange thing. How does your labor income affect my labor income? Well, we are economists, so we can always come up with a model in which it does so. But here, this is saying that the endogenous effects are going to show up not in the outcome equation, but in the best response equation, and in an inevitable way, provided that phi is not equal to 0. Now, this might still bother you, and Josh is not here to sort of express his viewpoint, so I will channel Josh here. And he says, well, this doesn't make sense, because how is it that, what you do at the moment affects what I do at the moment? What is the sort of the usual causality channel here? Well, I don't think that's a bad question. It's I'm choosing my schooling at the same time as you're choosing your schooling. So this is a Nash equilibrium. So in a Nash equilibrium, formally, we're both making our choices exactly at the same instant. So how is it that what math does affects what I do? Well, this is what game theory says. But game theory says it in a very refined way. It doesn't say that actual choice that math does affects me. It says that my expectation of what math does affects me. So there's a slight difference, and this does matter for some empirical issues. But I think it's unavoidable as long as you're going to be game theoretic about it. And again, what I'm wanting to argue, even if it's going to make me sound like a broken record, I think if you're really interested in these issues, you cannot avoid the game theoretic interactions over networks. The second interpretation is that perhaps we should think of this as a dynamics of a stationary distribution. So if you don't like x affects x, Justin's current decision affects my current decision. If you may not like that, there's something perhaps a little fishy about that. But what you can do is that you can write exactly the same equation, but now dynamically, except that I've made a typo. But I actually meant to put t-1 for the externalities. So the effects from the externalities come from t-1 from your last period's choice. And then you do the best response dynamics of this. So the environment doesn't change, but choices change. Then the best response equation is going to look like this, exactly the same as before, except that I have t on the left-hand side and t-1 on the right-hand side. And then the Nash equilibrium that I just characterized corresponds to the stationary distribution of this dynamical process. So in some sense, if you don't like the x currently affects x, if you give it somewhat of a dynamic interpretation. Now, if you have the dynamic interpretation and longitudinal data, you might want to exploit that. But but even if you don't have the longitudinal data, the game theoretic interactions would still translate into a stationary distribution in which the endogenous effects are sort of interpretable and work out in one way or another. Okay? So now, do the simplifying assumptions here matter? Of course they do. The quadratic and all of this perfect information. But at some level, they don't really matter for the big picture points that I'm trying to make. If you want to generalize this, you can put, instead of a linear game, you can put a nonlinear game. Some nonlinear games are going to look like this one already. Even more nonlinear games are going to be quite well behaved under some assumptions. So for example, there's a very nice paper by Nizar Aloush, which looks at these. And you have best response equations that are still interpretable. And you can have minimal uniqueness conditions, which are again related in terms of the same sort of objects. You can also think that for all of these random error terms, being known for everybody is not so reliable, so reasonable. So you can do like Matt's paper with Galeotti, Goyal, and Yariv in Review of Economic Studies and put incomplete information. Again, a lot of the insights at the level that I'm sort of specifying generalize. But of course, when you come to estimation, you have to do different things. And I'll talk a little bit about that when I come to the specific application. Okay. So what are the identification challenges? Well, ever since the work by Deaton and Mansky, it's sort of very well understood that there are reflection-related problems and other problems in the identification of these sorts of externalities, both of the contextual and the endogenous effect variety. Throughout here, when I'm talking of identification, I'm not referring to the lack of identification of the relevant regression parameters. I'm talking of the identification that you get some regression parameter, but you don't know what that regression parameter actually means. It doesn't correspond to underlying structural or causal numbers, estimates. So, so let me sort of be a little bit more specific about this, although I don't know that how much more detail I want to give. So for instance, the regression that the simplest regression that you can run here is going to be something like, not here, meaning not in this context of this model, but in this context of these general issues, is going to be something like I regress yi on my xi, so there's a b own effect, and then there's a b spillover effect, which is this x bar i. Now, this problem is already hard enough. It's hard enough because, as people understood, long ago, and a specific version of this sort of Josh and I tried to develop in our paper is that, even if there are no externalities, if you run this regression, this B spillover number will not be estimated to be equal to 0. And for example, it's going to be different if the OLS estimates of own effects differ from the IV estimates using group dummies, if there are differential measurement error, all sorts of things. And all of these problems become harder when you have the endogenous effects, for example, group means of outcome variables on the right-hand side. So these problems are all well understood. That doesn't mean that we have great solutions to them, but they at least there are some approaches for dealing with them. Instead, what I want to emphasize are two other problems. One of those is also sort of somewhat well understood, but I want to emphasize it because it's going to come back. And I think the sort of the best way of thinking about this is through Bruce's here also. Bruce Sacerdote's very nice QJE paper in which he looks at random assignment and random assignment of students, and then he finds that their outcomes are correlated. So if I'm randomly assigned to another student who has low GPA, well, I tend to have low GPA. But this result, though very interesting, and though that it does identify the effect of the sort of the correlation structure in the data, what does it actually say when the effects are, whether the effects are contextual or endogenous? Well, it's very difficult to say because in particular, if I run a regression like that, these error terms are going to be correlated. So essentially, you can think of what Bruce's regression doing is that it's running a regression like this, and it has randomized assignment of individuals, so you can think of this y bar as being as randomly assigned. But that doesn't solve the identification problem because the error terms are also potentially correlated. So for example, if I am assigned to Matt as my roommate, but we both happen to be in a room that's above the train station, the train's going to go over all night, and neither of us are going to study, neither of us are going to be able to sleep. We're both going to have low GPAs, but it's not really an externality. It's an example of the correlated effects. So I'm emphasizing this because the key issue that we have to deal with when we come to these games over networks are these correlated effects. And these correlated effects are going to be endemic because just the nature of being friendships is that you're going to spend time together, you're going to be in the same place, or it's going to be geographically in the same place. And also the endogenous networks, I'm going to be friends with Matt, and this is already he emphasized in the context of homophily, only if we have some characteristics together, which might be then create a correlation in the error terms, or might be the source of our differences from other units in the study. Now, the other thing that I want to emphasize is, I think, slightly less well understood, but I'm sure other people have run into it, is that even ignoring these things, the fact that all of this is underpinned by a game also creates some special endogenous, special identification challenges. To do that, let me take the best response equation. Again, let me forget about corner solutions, since none of what I'm saying is particularly modified by corner solutions other than becoming more complicated. So this was the best response equation. Xi depends on other people's x's. Take this, and this was the outcome equation, and put this x into the outcome equation. And then cancel terms, and then what you end up with is this equation 8. Now, this is the outcome equation when people actually behave according to the Nash equilibrium of the game. Now, what you'll see is that some of the important parameters that you cared about have actually disappeared. So in particular, you care about the own effect that has disappeared, and you care about this strategic complementarity, strategic substitutability that has disappeared. Instead, you have a quadratic relationship between y and xi squared. Whether it's quadratic or not, I don't think that's so super important. But the coefficient is something entirely different from what we were looking at, which is it's now replaced by the marginal cost of the effort level. So in other words, at the beginning I said you could take this outcome equation, perhaps you could try to estimate the parameters of this equation through some nonlinear least squares. So what this says is that if this is in fact an outcome of a game theoretic interaction, you can't do that. Even if you have exogenous sources of variation in xi, as long as there is some residual choice, that won't be possible, because people are going to make their choices in such a way that it exactly nullifies some of these effects, and both alpha and phi have totally disappeared. Now, at this point, you might say, well, I knew this network stuff was too complicated and unnecessarily complex, and we should just go home and forget about it because we have no way of dealing with it. But actually, you can get identification here. What it requires is that it requires you to estimate this equation 8 jointly with the best response equations. Because if you did that, from equation 8, you identify theta and the spillover effect, some local average treatment of gamma. And then once you know theta, from the intercept of the best response equation, you identify the own effect. And from the slope of the best response equation times theta, you identify the strategic complementarity. So there is enough information in the data to identify the parameters that you want, but it requires that you estimate these two jointly, or you can estimate them as single equations, but you do the inference on them jointly rather than just focus on the outcome equation. Okay? So, so is this feasible? Well, let's get a little bit more deep into it. So now the next challenge that we have to face here is how are we going to make it operational to exploit this network structure together with the endogeneity of the x's. And I'm going to talk about two approaches here. The first one is a really actually, let me come back to this slide. I don't need this slide now. Let me first talking about network structure here, and then I'll come back to that slide. So it's a really nice, a very creative paper by Bramoulet, Lejabri, and Fortin in the Journal of Econometrics, and it is essentially uses the following idea. The idea is that you can use assuming that the network is known, and I'll come back to that in a second. So for the next 5 slides, I'm going to assume that the network is known. So assuming that the network is known, you can actually use the structure of the network, in particular parts of the network that has sparseness in it, in order to get identification. And the idea goes something like this. So imagine that you take a triangle, Kalle, Matt, and myself. If I am friends with Kalle and I'm friends with Matt, but the two of these guys are not friends together, then anything that is a characteristic of Kalle that affects his education choices through the strategic complementarity or strategic substitutability will also affect game theoretically my education choice. But it won't affect Matt's choice because they're not friends. So therefore you can use that, one affects Matt's choice conditional on my choice, because the only channel of influence between them is through me and Matt. So using that idea, you can use Kalle's characteristics as an instrument for my education to look at the impact of my education on Matt's education. So that's essentially the idea which is written here in a slightly more mathematical form. Now this also works if Kalle and I have correlated error terms, but it crucially requires that there should be no correlated error terms between Matt and Kalle. And the idea there is that, well, these guys are not friends, and perhaps they're not friends, they should not be, they didn't choose to be friends, and there is no natural for homophily to kick in. Perhaps they're not friends, and as a result, there is no reason for them to have naturally correlated error terms. Now, I think that reasoning is not fully compelling, however. Well, it's not fully compelling because, you know, if the three of us have this triangle of friendship, it's likely that we live in the same locality, or we are at least hanging out in some usual places. So any geographic correlation structure is going to affect things. And it's also difficult to come up with error structures, or you could come up, of course, it's feasible, but it's difficult to think that plausibly I'm strongly correlated with Kalle because I'm friends, I'm strongly correlated with Matt because we are friends, but these two guys are not correlated. So that may not be too super plausible either. So in other words, this idea of exploiting network structure, I think there are some interesting ideas here, but these correlated effects really make it that what you come up with is often going to have the sort of difficulties of interpretation that I tried to highlight using Bruce's roommate example. Now, another idea is to come up with instruments. Of course, if you can do that, that's great. But in this context, I think instruments have to have some additional special features. So in particular, the idea here is come up with an outside instrument, something that changes, that affects, that's not related to the network and affects Kalle's choice. Then that could be an instrument for Kalle's behavior when I look at his impact on me and so on and so forth. Now, the idea is that if these network instruments are really outside variables and they're really orthogonal, they're randomly assigned to Kalle, there are good reasons, depending on the setting, that they might also be orthogonal to the network. But if they are orthogonal to the network, then you can take products of that with the network matrix, and they'll be orthogonal to me and so on and so forth. So in fact, if you have an outside instrument that is not only just orthogonal to yourself, but is also orthogonal to the network, then you can take the products of that with the network matrix, and it's going to be an instrument for lots of other things in the network. So that's sort of the idea. Now, is it important that in all of this the network is known? Now, in the Bramule et al. Thing, it's actually not trivial that the network is not known. Because if the network is not known, it could be a problem because there could actually be a link between Matt and Kalle, and I think there is no link, and then I use Kalle as an instrument, and that's going to call it invalidity. But in this idea, in this network instruments idea, you don't actually need the network to be known. It could be unknown up to some parameters, and then you can estimate those parameters. You do need to have some structure, because otherwise you're back to estimating n times n minus 1 parameters, or n square parameters, depending on whatever it is. So that's not great. So let me try to give you an application of this from a paper that I wrote. And what I want to emphasize here is not the details of the paper, but how this thing can be operational. So this is a paper with Camilo Garcia Jimeno at Penn and Jim Robinson at Harvard. And essentially what we're interested in is the effect of state capacity, like for example, the local state capacity. Does municipality have employees? Does it offer certain types of services on public good and prosperity outcomes in a municipality, but recognizing that it's going to create spillovers. Health or law enforcement or judicial things are going to create spillovers. And so here you can think of this as a network game. The G matrix is going to be the municipality network with some unknown cost parameters. And then we're going to apply this to Colombia using municipality level data from Colombia, which is a good setting for several reasons. One of them is that these issues are generally viewed to be important in Colombia: lack of state capacity, lack of local services, and so on and so forth. And secondly, the specific way in which the local state developed, going back to colonial times, gives a potential candidate for these sorts of instruments. Okay, so what's the model? The model is exactly so this is the context that I just mentioned. It's a very large country split by the Andes, lots of places in which there's very little state capacity, and that's been true historically and so on and so forth, but given that time is short, let me not dwell on it. The model is identical to the one that I have talked about with just some small changes, except that the Gij is equal to 0 for municipalities that are not neighbors, and for municipalities that are neighbors is a function of the distance between them and the elevation. So how rugged is the terrain, how difficult it is to reach one to the other. These parameters here, delta 1 and delta 2, could be unknown. And then what about instruments? Well, there are no perfect instruments, but in this case, the way that the colonial state sort of expanded sort of gives you some interesting sort of ways of doing things. And let me actually focus, given that the time is short, on this royal roads. These royal roads are essentially one of the few investments in infrastructure that the colonial authorities did. They built on the existing Inca roads, but they were very, very idiosyncratic, and essentially they soon disappeared. So the royal roads were important in determining where the colonial state went, where they decided was where their garrison and so on and so forth, but they have nothing to do with the current network structure, current road network, current transportation structure. So at least it's a candidate, and then it turns out that it's sort of rather well behaved on certain things. It's not really related to current roads, and so on and so forth. So what I'm trying to sell here is not that this instrument is valid, but just the general concept. So imagine that this instrument is valid. And but the other thing that you really want is that even if you have a prior that this instrument is valid as a source of variation, it might still create a problem. And this problem was on the slides, but I skipped it because time was short. So I want, which is that the concern that you have is about this correlated error terms. So it just so happens that these instruments are themselves spatially correlated. They're correlated over the network. Then correlated error terms are going to project over them. So one other desirable feature of this sort of instruments that you want to use in a network setting is that it's not really mimicking the network structure itself. So here is the correlation matrix for distance to royal roads, colonial officials, and colonial state agencies, and then looking at it neighbors average. So for the royal roads, it's a geographic variable. Of course, it's going to be a little bit positively correlated. But if you look at the other one, colonial officials and the colonial state agencies, it's very uncorrelated with the neighbors. So it's at least prima facie, it has these properties that it's creating variation. It's not related to the current network, and it's plausibly sort of plausibly exogenous. So how do we then go about estimating this? So one thing you could do is you could take these things, and I'm doing it just in the paper we have many more outcome variables. So, but I'm doing it for the first stage number of municipality employees, and these are the best response equations. So the first thing you could do is that you could estimate the best response equations one at a time. So not really do systems identification, which is use the outcome equation and the best response equations at the same time. Or you could do the outcome equation and the best response equation at the same time using GMM or some other nonlinear method. So let me just focus on this column or sorry, let me just focus on this column and this column. So you can see, and this is a very robust result, when you do this best response equation, you always get evidence for strategic complements. That in places where your neighbors invest more in state capacity, you seem to be investing more in state capacity yourself. And that's robust when you do estimate things nonlinearly. And then this is the prosperity equation, the second outcome equation. Now I'm looking at the fraction of the population that's not in poverty, and this is the own effect, and this is the externality effect. So you have both the own effect and the externality effect precisely estimated, and you see that the GMM gives very similar results. And, and the own effect is larger than the externality effect. But of course, the externality effect is on several neighbors, so it's you want to scale that up. But instead of scaling it up right now, I'm going to do a thought experiment. So one advantage, so until now, this wasn't the selling point of motivating the games over networks. My argument is that you really have to take the games over networks seriously if you're going to think about these externalities. There really isn't any way of avoiding it. But once you take them seriously, then you can do more interesting counterfactual exercises. So just to illustrate that, let me just do one counterfactual exercise, and then I will conclude, which is, let me take, as I said, in Colombia, this municipalities, out of those 1,000 municipalities, more than 500 or almost 500 of them are very, very, very low state capacity. So let me take a very radical policy and take all of these very low state capacity, very few number of services and employees relative to population, and take them to the median. And then this is the first panel. You take them from you take all of these municipalities and you bring them to the median. Of course, the median doesn't change, but the fraction of the population that's not in poverty goes up from 57 to 60%. So that's a pretty large effect. And then you can do a decomposition and you can say how much of this is due to own effect and how much is due to spillovers. So the spillovers are not implausibly large, but they are large. They're not trivial. So they account for about 40% of the effect. But this exercise is actually partial equilibrium. It doesn't take into account that once you do this change, through strategic complementarity, other places are going to respond also. So one advantage of the game theoretic model, then you can say, well, actually, let me do the full equilibrium, which is that once I do this policy experiment, let other municipalities that weren't directly affected respond to it because their neighbors now are affected, and because of the strategic complementarities, we could have done the same thing if it was strategic substitutes, but in this case it's strategic complementarities, they're going to adjust also. Now you do that, now you get a whopping increase from 57 to 68. And moreover, about 75% of this increase comes from the network effects, which is that these municipalities are responding. Now, should you take these numbers seriously? Well, they turned out to be very robust, but they're based on a lot of assumptions. So what I want to emphasize is not that you want to believe these numbers, but I think once you take the networks interactions over these networks seriously in the context of externalities or peer effects, you can do a lot of interesting stuff, and there's still things that can be done. And moreover, none of this depends on linearity. So in the paper, we actually do a lot of things non-linearly. Then you can do the nonlinear estimation. So as I said, the linearity matters for the specific equations, but the idea generalizes. So I want to sort of summarize. So I want to conclude by just saying one final thing, which is that in all of this, I took all of the sort of the various challenges, but I've stayed away from one of them, which is going to come now in the next lecture, which is the endogenous networks. So all of the issues I have emphasized are present even when the networks themselves are not endogenous, but they get multiplied when they are endogenous. But they also become even more interesting, and some additional interactions come in. And let me sort of talk about just a paper by Carell, Sacerdote, and West, because I think it illustrates some of the issues with the endogenous networks very nicely. So essentially what these guys did is that they estimated peer effects across cadets in the US Air Force Academy, and then they found that there are these peer effects, and I think it's a fairly convincing paper they have in Jolly, and they also repeat that in part of their this paper that I'm mentioning in Econometrica, but also moreover these are nonlinears. High ability cadets create more externalities on low ability cadets, but low ability cadets don't create much of a negative externality. So on the basis of these nonlinear externalities, they said, well, there is an optimal way of organizing these squadrons so that we can try to maximize the exposure of the low ability cadets to the high externality creating high ability cadets. And they somehow, I don't know how they did this, they went and convinced the US Air Force Academy to allow them to do the randomization based on the solution to the optimization problem that they solved. And as a result, they generated squadrons that were essentially, at least a treatment group, that were designed to maximize this externality. And then they went and they tested the result, waiting to find or expecting to find a large positive effect, and they find exactly the opposite. Now their treated squadrons had negative outcomes for low ability kids. What happened? Well, I think what happened, is a good lesson in taking the endogeneity of the networks and again the networks perspective even more seriously. So what happened is that in creating these squadrons that maximize exposure of low ability guys, they created a lot of bimodal squadrons in which there are lots of low ability people and then lots of high ability people without middle people, because the middle people are wasted according to this objective function. You want to replace the middle people with additional low ability people so that they can get the exposure to the high ability people. But then what they found in their follow-up sort of surveys and investigations is that without the middle, this bimodal squadrons had an entirely different form of social network interaction. So when the middle people were there, the high ability and low ability interacted, but when the squadrons became bimodal, now the interaction structure changed because people now sorted to the low ability or the high ability group. So this really cut the externalities from the high ability to a low ability. So this sort of highlights a very simple but very beautiful example of something more general, that if you actually want to take these games now seriously together with the endogenous network formation, whenever you change policy, you might actually change the network formation with quite important implications for what the conclusions will be. Okay, I'll just stop there and take some questions, even though I'm a little bit over time.